Welcome to the deep dive. We take your sources, your research, our notes, and boil it all down. And today, we're diving headfirst into something that, honestly, should make everyone listening sit up straight.
Yeah.
It's broken access control. And get this, it's not just on the OWASP top 10 list for 2021. It is number one.
Number one, yeah. That's a huge jump, right? It was 5th back in 2017.
Exactly. Fifth to first. That really screams major, major problem.
And what's really striking, looking through all this material, is just how widespread it is. We found this stat that's, well, it's pretty shocking. 94% of applications they tested had some kind of broken access control.
94%. Wow.
Yeah, and an average of nearly 3.81 vulnerabilities per application. It's not rare. It's alarmingly common.
That number alone is a massive wake-up call. It's like finding a huge hole in almost every digital fence you look at. So, okay, for this deep dive, our mission is basically to cut through the jargon, give you the shortcut to understanding what this thing is, why it's everywhere, how attackers use it, and crucially, how to actually stop it.
Right. And maybe I should start by quickly clearing up authentication versus access control, because people mix them up all the time.
Good idea. Yeah.
Okay, so authentication, think of that as checking your ID. The bouncer at the club looks at your driver's license, confirms who you are. Yep, you're on the list.
Okay, makes sense. Who you are.
Then access control or authorization. That's what you're allowed to do once you're inside. That same bouncer might say, okay, you can go to the main bar, but sorry, no entry to the VIP lounge. Or here's the key to the coat check, but not the key to the manager's office.
Got it. So authentication is the who, access control is the what you can do.
Exactly. And when that bouncer gets confused or the keys are all messed up and anyone can just walk into the back office, well, that's broken access control. Chaos.
That clears it up perfectly. So let's dive in. When we talk about broken access control, what's actually, failing and why the massive jump to number one?
Well, at its heart, it happens when an application just fails to properly enforce those rules, those restrictions on what someone can do or access. And this could be someone who's logged in, an authenticated user, or sometimes even someone who isn't logged in at all.
So like you log into your bank and suddenly you're seeing someone else's account details.
That's a pretty terrifying, but yeah, accurate example. Or maybe you could initiate a transfer from their account. That's access control completely failing.
Right. So an attacker could potentially read private data, do admin stuff as a regular user, mess with data they shouldn't even see, or even take over the whole system.
Absolutely. The potential for damage is just enormous, which brings us back to why it shot up the OWASP list.
Yeah, why now?
A big reason seems to be how easy it often is to exploit. You don't necessarily need fancy hacking tools. Sometimes just a web browser, maybe tinkering with the URL.
Really? Just a browser?
Often, yes. Or a basic HTTP client. That low barrier to entry, combined with the potential for, catastrophic results, massive data breaches, huge financial hits, regulatory fines like GDPR, it makes it incredibly attractive to attackers.
Low skill, high impact. That's scary. Yeah, that's scary. So why should you, listening right now, really care? Well, like we said, it's everywhere, 94%. It's often easy to exploit, meaning apps you use daily could be vulnerable. And the effect on your privacy, your security, the trust you put in these services, it's fundamental.
It really is. This isn't some obscure theoretical flaw. It's a clear danger in so many applications.
Okay, so let's get into the specifics. What does this broken access control actually look like? It's not just one thing, right? It's kind of a family of issues.
Exactly. There are different ways these systems can break down. We don't need to get lost in all the academic types, like role-based or attribute-based, but it's useful to see how they fail in practice. And one of the most common and I think sort of insidious types is called insecure direct object references. IDOR for short.
IDOR.
This is where an application exposes its internal IDs, like a user ID number, maybe a document ID directly in the URL, or maybe an API call.
Like example.com user123.
Precisely. And an attacker just changes the number. They try 124, 125, and suddenly they might be accessing someone else's stuff.
Okay, and this is where it gets really chilling. The example from our sources. Imagine an online shop. You're looking at your order history. The URL is something like AP orders 123.
Right.
An attacker just changes that 123 to 124. And boom, they're seeing someone else's orders, their address, maybe payment info snippets, what they bought.
Yeah, exactly. It's terrifyingly simple sometimes. Just change a number in the address bar.
Yeah.
Huge privacy implications from such a small change.
Wow. Okay, what's another common one?
Missing function level access control. This is where the application doesn't check if you have permission to use a specific function or feature.
How does that work?
So imagine there's an admin panel. The link to, say, admin settings or administers might be hidden from your normal user view. You don't see the button.
Right.
But if you, as a regular user, just type that URL directly into your browser, admin settings, and the server doesn't actually stop and think, wait, is this user an admin? Then you may just get in. Suddenly, a regular user could be deleting other users or changing important settings just because that server-side check was missing.
Even though the button wasn't there? That's sneaky.
It relies on security through obscurity, which is never real security.
Okay. Then there's CORS, cross-origin resource sharing. This sounds technical.
It does, but the concept is pretty important. Basically, your browser is naturally protective. It doesn't like websites just randomly grabbing data from other websites you might be logged into.
Right, like my email grabbing stuff from my bank. Bad idea.
Exactly. So when one site, say evil.com, tries to make a request to another site, like your-important-api.com, using your browser, the browser first asks your-important-api.com, hey, is evil.com allowed to make this request?
Okay, a permission check.
Yes. Chorus policies are the answer your-important-api.com gives. Now, if that API is configured badly and says, basically, sure, anyone can ask, often represented by access control allow origin, that's a huge problem.
The star means everyone.
Pretty much any origin. So the example our source gives, a malicious website you visit could send requests in the background to a sensitive API you're logged into using your session cookies. Because of that policy, the API responds, and the malicious site can read your private data. Data theft happening silently.
Yikes. Okay, so bad CORS is like leaving the door wide open for other websites.
That's a good way to put it. And then there's forceful browsing.
Forceful browsing. Sounds like someone just trying random URLs.
That's basically it. Attackers just guess paths. They try things like backup or config or maybe admin, and sometimes they hit gold. They find something like backupdatabase.sql or config.json just sitting there, unprotected.
You're kidding. People leave database backups just open.
It happens more often than you'd think. Maybe it was temporary, maybe someone forgot to secure it, but finding that can expose database passwords, API keys, everything.
It sounds almost negligent, but I guess under pressure, mistakes happen.
They do, and there are others too, briefly. Things like manipulating hidden parameters, changing role user to role admin in the data sent from your browser, hoping the server doesn't double check.
Right, trusting the client too much.
Exactly. Or sessions not being reset properly if your role changes. Or API tokens that are meant for one small thing, like reading a profile but accidentally have permission to delete things because their scope wasn't limited.
So looking at all these, IDOR, missing function checks, bad CORS, forceful browsing, parameter stuff. What's the root cause? Why do these keep happening?
A lot of it comes down to a few core issues. Trusting data or controls from the client side is a big one, not validating every request on the server, using those predictable IDs we talked about for IDOR, simple misconfigurations in things like CORS or file permissions.
And maybe not having a central place to manage all these rules.
That's huge too. Lack of centralized enforcement. Different teams doing access control differently, leading to gaps and, just human error. The Flask code example we found is quite telling. A function getToSer just fetches user data based on the ID provided. There's no check at all to see if the person making the request is allowed to see that user's data.
So it's like a library just handing out any book to anyone who asks for it by number without checking their library card or if the book is restricted.
Exactly. It checks what you asked for, but not if you're allowed to have it. That authorization step is missing. It's that second check that's so often forgotten.
Okay, that really clarifies the underlying problem. Let's make this real. You mentioned breaches.
Yeah.
The Facebook one from 2019 seems like a perfect, if unfortunate, example.
It really is. September 2019, it affected, estimates vary, but around 50 million accounts, exposed private data, phone numbers, email addresses. It was significant.
And it all stemmed from their View As feature, right?
Yeah.
Which, ironically, was meant to be a privacy control.
Precisely. The feature let you see what your profile looked like to someone else, a friend, the public, etc. It was supposed to enforce access controls, but the way it was built, well, there were flaws.
What went wrong? How did View As lead to a breach?
It was actually a chain of vulnerabilities, which is often how these big breaches happen. First, the View As feature, when used, generated these things called access tokens. Think of them as temporary digital keys.
Okay.
But crucially, these tokens were generated with more permissions than they should have had. They weren't just limited to viewing a public profile, they had broader access.
So the key opened more doors than intended.
Exactly. Then second, there was an API endpoint, basically, a specific web address the Facebook app used that was involved in this feature. And this endpoint failed to properly check the scope of the access tokens being used.
Scope meaning what the token was allowed to do.
Yes, so you had this overly powerful token, and the API endpoint wasn't double-checking, hey, is this token actually allowed to do what it's asking to do?
Ah, so the powerful key met a lock that didn't check the key's limitations properly.
You got it. Attackers figured this out. They could use the View As feature to get these powerful tokens and then use those tokens against the vulnerable API endpoint to access private information of other users, essentially taking over their sessions. They could cycle through user IDs, 123, 124, 125, using these tokens to pull data they absolutely shouldn't have seen.
Wow. So what was the fallout from that? 50 million accounts is huge.
Massive data exposure, potential for full account takeovers, although Facebook said they didn't see evidence of that widespread. But the regulatory impact was severe. They got hit with a $5 million fine from Ireland's Data Protection Commission under GDPR.
Not insignificant.
No. And the reputational damage, the cost of fixing it, they had to disable the feature, force logouts, reset tokens for millions. It was a huge mess.
So what are the big takeaways from the Facebook breach? The lessons learned.
Number one, always validate the scope of access tokens. A token for viewing shouldn't allow anything else. 2, the principle of least privilege is critical. Give components and APIs only the absolute minimum permissions they need. 3, rigorous testing, especially for features touching access control and covering edge cases like View As.
Don't forget the basics.
Right. And 4, automate detection where possible and strive for centralized, consistent access control logic across your entire application, especially all your APIs. Don't let different parts handle it differently. The Facebook incident really drives home why these seemingly small details are so critical.
Okay, so we've seen how bad it can get. Let's pivot to solutions. How do we actually build systems that don't fall prey to this? It sounds like it needs layers of defense.
Absolutely. It's not just one fix. It's a combination of secure coding habits, smart architectural choices, and ongoing testing.
Let's start with coding. What's the golden rule?
The absolute non-negotiable rule is enforce authorization on the server, always. Never trust the client. Don't rely on hiding buttons in JavaScript or hidden form fields. Attackers can bypass all that trivially.
So how do you do that server-side check effectively?
Well, in frameworks like Flask, for example, you use something called a decorator. You might write at requires role right before the code for a sensitive admin function. That decorator acts like a checkpoint. Before any of that function's code runs, the server checks, does the current user actually have the admin role? If not, access denied. Simple, effective, and done on the trusted server.
Makes sense. What about preventing that IDOR stuff, the insecure object references?
2 main things. First, try to use indirect references instead of sequential IDs like 1, 2, 3. Use things like UIDs. Those long, random-looking strings, they're much harder to guess.
Okay, use UIDs. Is that enough?
Not entirely. Even with a UUID, you still need to check if the user making the request actually owns or has permission to access that specific resource. So after finding the object using the UID, you need an explicit check. Like in Java, you might have requesting user.owns resource or requesting user.access resource.
Ah, so it's a 2-step process. Find the thing, then verify permission for that specific thing, for that specific user.
Precisely. It closes the loophole where someone might guess a valid UUID but shouldn't be allowed to see it. It's that crucial authorization step again.
Got it. What else on the coding front?
Secure session management is vital. When a user logs out, or critically, if their role changes mid-session, like being promoted to admin, you must invalidate their old session immediately. Otherwise, they might keep old privileges.
Right. Prevent lingering permissions.
And use secure, unpredictable session IDs. Python's secrets.tokenRLSafe is a good example for generating those. Oh, and always sanitize and validate any input coming from the user to prevent them from sneaking in things like role admin. Never trust client input.
Okay, moving up a level to architecture. What are the best practices there?
A big one is using a centralized access control system. Instead of every developer implementing checks differently, use a standard mechanism like role-based access control, RBAC, or attribute-based access control, ABAC.
How does that help?
It ensures consistency. Frameworks often help here. Like in Spring Security, using an annotation like @preauthorize as role applies a check defined in a central security configuration. Less room for one-off errors.
Centralized rules. Good. What else?
The principle of deny by default. This is fundamental. Your system configuration should block everything unless access is explicitly granted. Think of a web server like Nginx protecting a sensitive directory. You'd have deny all first, and then allow only specific trusted IP addresses or authenticated users.
Deny first, allow second. Makes sense.
Also, secure your API endpoints properly, ensure they require authentication and authorization, and use those scoped tokens we talked about earlier, like OAuth 2.0 scopes, read.user, write.order, so a token can only do exactly what it's intended for.
And for CORS.
Lock it down. Don't use the wildcard sake. Explicitly list only the domains that absolutely need to make cross-origin requests to your API. In Node.js with Express, that might look like app.use. Only allow what's necessary.
Right. Be specific.
And finally, think about deployment and configuration. Simple things, like disabling directory listing on your web server. Stop that casual, forceful browsing. Use secure frameworks that handle a lot of this for you. Django, Spring Security, etc. Don't reinvent the wheel badly.
And checking things regularly.
Yes. Regularly audit your configurations, your firewall rules, your access control policies, and set up robust logging. Log every access attempt, successful or failed. That way, you can monitor for suspicious activity and hopefully spot an attack in progress.
Okay, so we've built our fortress, hopefully with strong walls and good guards. How do we actually test it? How do we find holes before the attackers do?
That's where the security toolkit comes in testing, testing, testing. You need a mix of automated and manual approaches.
What kind of automated tools are useful here?
There are quite a few. Tools like Burp Suite are fantastic. Its intruder tool is great for automating those IDOR tests you feed it a list of IDs, and it checks the responses. OWASP ZDAP is another powerful one, an open-source dynamic scanner that can automatically probe for many vulnerabilities, including missing access controls.
So they actively poke at the application.
Exactly. Postman, while often used for development, is also great for manually testing API endpoint permissions. You can easily craft requests and see if you get access you shouldn't. And then there are tools like Snake, which look at your code and dependencies for known vulnerabilities or common misconfiguration patterns related to access control.
But automation can't find everything, right?
Definitely not. Manual testing is crucial for finding more subtle or business logic-related flaws. For IDOR, the classic test is logging in as user A, copying a request URL or API call for their data, like a pip profile 123, then logging in as user B and replaying that request, maybe changing the ID of pipe profile 123 again or trying 124. Does user B see user A's data?
Ah, the direct comparison test.
Exactly. For forceful browsing, you can use automated tools like Derb or GoBuster to guess common directory and file names, but also just manually exploring, trying admin, backup, test, config, etc.
What about testing those function level controls?
That's privilege escalation testing. Log in as a low-privilege user, then try to directly access URLs or call API functions that should only be available to admins. See if the server stops you. You can also try manipulating those parameters we mentioned, like changing role user to role admin in a request.
And testing CORS.
You can set up a simple web page on a different domain and write some JavaScript to try and make requests to your application's sensitive APIs. Check the browser's developer console. Does the request succeed when it shouldn't? Are the access control allow origin headers too permissive?
So lots of hands-on probing. Where does this fit into development? Is it just a final step?
Ideally, no. The best practice now is shifting left integrating security testing into the CI/CD pipeline. Continuous integration, continuous deployment.
How does that work?
You can use static analysis security testing or SaaS tools like SonarQube. They analyze your source code before it's even run, looking for potential flaws, including access control mistakes.
Catching it early in the code.
Right. And you can also integrate dynamic analysis security testing, or DAST, tools like ZAP or Burp Suite Scanner into your pipeline. After an automated deployment to a test environment, the pipeline could trigger a scan to actively check the running application for vulnerabilities.
So security becomes part of the automated build and deploy process.
Exactly. It makes security continuous, not an afterthought. catches issues faster, makes them cheaper to fix.
Okay, looking beyond the common stuff, what's on the horizon? What are the advanced challenges or emerging trends in access control?
Well, the move to microservices and APIs everywhere creates complexity. Instead of one big application with one set of rules, you have lots of small services, each needing its own access control. How do you keep that consistent and secure?
Yeah, that sounds messy.
It can be. This is where things like API gateways become really important. They can act as a central checkpoint, maybe enforcing authorization based on JWT claims, information embedded securely within the access token itself that defines what the user can do.
Centralizing the checks, even with distributed services. What about the cloud?
Cloud environments bring new risks. Things like server-side request forgery, SSRF, attacks targeting internal metadata endpoints can sometimes bypass traditional controls. And IAM identity and access management misconfigurations are huge. Giving a cloud function or service overly broad permissions is a common way access control breaks down in the cloud.
Are there tools for that?
Yes, cloud providers offer tools. AWS IAM Access Analyzer, for example, can help you identify overly permissive roles or policies by analyzing who can actually access what.
Good to know. Any other big trends?
Zero trust architecture is a major one. The core idea is never trust, always verify. Don't assume that just because a request comes from inside your network, it's safe. Every request needs to be authenticated and authorized constantly.
Continuous verification.
Right. We're also seeing AI being used by attackers to exploit vulnerabilities like IDOR more effectively, automating the discovery process at scale. And securing serverless functions like AWS Lambda presents unique challenges, as their execution roles need to be carefully scoped to avoid giving them too much power.
Wow. So the landscape is definitely still evolving. Okay, phew, that was a really comprehensive journey through broken access control. From what it is to why it's, number one, the scary ways it shows up like IDOR, the Facebook breach is a case study, and critically, how to prevent and test for it.
It really covers a lot of ground.
Yeah.
And the key takeaway has to be that this isn't some niche, complex attack. It's fundamental. It's the digital equivalent of having locks that don't work properly. And as OWASP confirmed, it's the top risk right now, often easy to exploit with potentially devastating consequences, as the Facebook incident showed all too clearly.
But, and this is important, it is manageable. By understanding these patterns, by building security in from the start with things like server-side checks and centralized policies, by using UUIDs correctly, managing sessions, locking down cores, and by testing relentlessly, we can build much stronger defenses.
Absolutely. It requires diligence, but it's not impossible.
So the final thought for you, listening, what does this all mean for you? As you use countless apps every day, clicking links, logging in, just pause and consider how many might still have these kinds of hidden flaws, these broken locks.
Yeah, given how basic some of these flaws are, like just changing a number in a URL and how widespread OWASP found them to be, how much of the internet's essential plumbing, the stuff we rely on daily, might still be vulnerable, just waiting for someone to check the wrong door or turn the wrong key. It's definitely something to think about.